A robot that cooks breakfast, wipes the counters, loads the dishwasher, and learns a new chore overnight is no longer science fiction. That is the promise surrounding Tesla Optimus Gen 3. But the problem is simple. The robot butler future is being advertised faster than it is being proven. Gen 3 is expected soon, yet cooking a full meal, cleaning a real kitchen, and completing 100 useful tasks in a day have not been verified in a normal home. So the real question is not whether Tesla can build a humanoid robot. It can. The question is whether Optimus is about to become a household helper or remain an impressive prototype with unfinished hands, limited training, and a huge production challenge. Right now, the Optimus most people have seen is not Gen 3. Tesla's public demonstrations are still centered on version 2 and the updated version 2.5 hardware, including the units shown walking more smoothly, sorting objects, and performing controlled tasks inside Tesla environments. That distinction matters because Gen 3 is expected to be a production-intent step, not just another lab prototype. It is the version Tesla has been aiming to reveal after earlier timing moved back, with the current target pointing toward late July or August of 2026. That schedule is important because it gives Tesla more time to improve the robot before showing it as something closer to the machine it actually wants to build at scale. The progress so far is real. Optimus has moved from awkward early walking to more stable motion, better balance, and more natural arm movement. Tesla has also shown units inside its own factories where the robot can collect training data, practice repeatable tasks, and operate in spaces Tesla controls. That is the safest place to teach a humanoid robot before asking it to handle messy homes. There is also the software layer. Tesla has demonstrated voice interaction connected to Grok, which suggests Optimus is being built around spoken instructions, not just pre-programmed routines. If that works reliably, the robot could eventually understand a request, ask a follow-up question, and choose the right action, instead of waiting for a button press. Still, Gen 3 should not be treated as the final Optimus. Tesla's roadmap continues beyond it, and humanoid robots will likely need several generations before they become common household workers. Gen 3 matters because it is supposed to move Optimus from impressive demo to useful worker. Cooking and cleaning are where a humanoid robot stops being a showpiece and starts being useful. A robot can look advanced while walking across a stage, dancing in sync, or carrying a box in a clean lab, but a kitchen does not care how impressive the demo looked. Cooking is a brutal robotics problem because almost nothing stays predictable. An egg can roll, crack, or slip. A pan handle may be hot. A tomato changes shape when it is cut. Oil spreads across a surface. Steam blocks sensors. A plate can shatter if the grip is too strong, but fall if the grip is too weak. Even a simple meal requires timing, tool use, force control, and constant small corrections. Cleaning has the same problem in a different form. Wiping a counter is not just moving an arm side to side. The robot has to see crumbs, liquid, edges, clutter, fragile objects, and the difference between a stain and a shadow. Loading dishes means recognizing shapes, avoiding sharp knives, stacking items without breaking them, and adapting when the dishwasher is already half full. That is why these boring tasks matter more than viral movement tricks. Fast walking proves mobility. Backflips prove extreme control. But homes need repeatable manipulation. They need a robot that can fold a towel the same way 10 times, carry a glass without spilling, clean around a charging cable, and stop immediately if a child or pet steps into the workspace. Tesla has not publicly shown Gen 3 cooking a meal or cleaning a home. So the claim that it finally does those things should be treated as the ambition, not as a confirmed milestone. The real standard is simple. Optimus only wins if it can perform ordinary work safely, repeatedly, and without a human rescuing it every few minutes. The hand is where Optimus either becomes a worker or stays a walking prototype. Tesla has previously shown robotic hands with around 11 degrees of freedom, meaning 11 independent ways the hand can move. But the long-term target discussed around Optimus has been closer to a 22-degree of freedom hand, which would allow far richer motion across the fingers, thumb and wrist. Tesla has also signaled that the design has changed, so the final Gen 3 specs may not match earlier public assumptions. The important point is the direction. More controlled motion in the hand, not just a stronger arm. That matters because most household chores are hand problems disguised as full-body tasks. Cooking requires a robot to grip a spatula, hold a knife at the correct angle, twist a jar lid, pick up a slippery bowl, and place a plate down without clacking it against the counter. Cleaning requires pinching a cloth, wrapping fingers around a spray bottle, pressing a sponge with the right force, and turning knobs that were designed for human fingertips, not machine clamps. A simple gripper can move boxes in a factory. A useful home robot needs fingers that can change shape around unknown objects. A mug handle, a fork, a towel, a banana, and a saucepan all demand different contact points. If the robot squeezes too hard, it crushes fruit or snaps plastic. If it squeezes too lightly, objects slide out of its hand. That is why tactile sensing, joint control, and software all have to work together inside a space smaller than a human palm. The hard part is not building one impressive hand. For a demo, Tesla has to design custom actuators that are compact, powerful, durable, and cheap enough to manufacture at scale. Those same actuator lessons affect the wrists, shoulders, hips, and the rest of the body. Every joint needs enough torque to do real work, enough precision to avoid damage, and enough reliability to survive daily use. One working hand in a lab is a milestone. Millions of hands coming off a production line with consistent performance is the real challenge. And even if Tesla solves that hardware problem, perfect fingers still do not guarantee a useful robot. The next bottleneck is the brain, whether Optimus can see, decide, and react instantly when the real world changes under its hands. The next version of Optimus needs a brain on the robot, not just a connection to one somewhere else. That is why Tesla's reported AI 5 chip matters. If it becomes the compute platform behind Gen 3, the goal would be to run the robot's perception and movement decisions locally, inside the machine. A humanoid cannot pause every time it needs to ask a server how to move its elbow. In a home, the world changes too quickly. Imagine Optimus lifting a wet cup from the sink. If the cup starts slipping, the fingers have to tighten in a fraction of a second. If it is wiping a counter and the sponge catches on an edge, the wrist has to adjust pressure instantly. If a dog walks under its feet or a person steps into the kitchen, the robot must change its path before contact happens. Those are not decisions that can depend on a perfect internet connection. Cloud systems can help with heavy learning, fleet updates, and long-term improvement, but the moment-to-moment control loop has to live on board. The cameras, joint sensors, tactile sensors, balance system, and language interface all need to feed into a local model that can turn messy, real-world input into safe motion. Voice control could become the most natural interface. A Grok-style assistant inside Optimus would let someone say, "Clean the table, then put the plates in the dishwasher," and have the robot ask a follow-up question if something is unclear. That is much better than tapping commands into an app for every chore. The problem is that voice interaction still has to become faster, more reliable, and more grounded in what the robot is actually seeing. A delayed or misunderstood instruction is annoying on a phone. In a robot holding a knife, a pan, or a glass plate, it becomes a safety issue. So the hardware brain is not just a performance upgrade, it is what lets Optimus react like a physical worker instead of a remote-controlled device. But the chip is only one part of the story. The bigger advantage may come from how every robot learns and how Tesla turns that experience into training data for the entire fleet. That is where Tesla's real bet begins. Optimus is not supposed to learn one robot at a time. The idea is closer to an Optimus Academy. One robot practices opening a drawer, folding a towel, sorting parts, or loading a dishwasher. Its cameras, joint sensors, force feedback, and mistakes become training data. Tesla improves the model, pushes an update, and every future robot starts from a higher baseline. The value is not just the task. The value is the lesson extracted from the task. This is the same flywheel Tesla used with cars, but the robot version is harder. A car mostly moves through roads built for cars. A humanoid has to deal with kitchens, tools, tables, shelves, clothes, cables, pets, and humans standing in the way. Every object can be shaped differently. Every home can be arranged differently. That is why structured practice matters before Optimus ever becomes a common household product. Tesla's factories give it a controlled place to start. At Fremont and Giga, Texas, Optimus can practice real work around repeatable processes, known parts, and mapped spaces. A robot moving battery components, carrying bins, inspecting items, or helping with simple line tasks can collect physical world data without the chaos of a private home. Engineers can measure failures, reset the scene, label outcomes, and improve the system faster. Elon Musk has also described a much bigger ambition: thousands of robots doing real-world practice, almost like physical self-play. In that vision, robots would continuously attempt tasks, learn from success and failure, and feed that experience back into the fleet. That is not a proven outcome yet. It is the Chief Executive Officer's stated direction for how Optimus could improve at scale. If Tesla can make that loop work, each robot sold is not just a product. It becomes another data collector, another trainee, and another contributor to the next software update. Then the question shifts. If Tesla can scale the learning, can it also scale the manufacturing, reliability, and price low enough for Optimus to leave the factory and enter everyday life? Musk has put a huge number on the table: a future Optimus production line capable of reaching 1 million robots a year. He has also described a long-term price target in the range of roughly $20,000 to $30,000 once production is mature and scaled. That price is central to the entire story. At that level, Optimus stops sounding like a laboratory machine and starts sounding like a product that could compete with a car, a major appliance, or a piece of industrial equipment. It would still be expensive for a household, but for factories, warehouses, and businesses, the math becomes more serious if the robot can work reliably for long hours. The manufacturing challenge is that Optimus is not a car with a different body shape. It has hands, fingers, wrists, arms, legs, actuators, sensors, gearboxes, batteries, computers, wiring, cooling, structural parts, and software-dependent calibration. Tesla has said Optimus contains thousands of unique parts, which means thousands of points where cost, quality, suppliers, assembly time, and reliability have to be controlled. It also needs a new production system. Tesla cannot simply drop humanoid robots onto an existing Model Y line and expect car-scale output. The company has to design fixtures, tests, assembly steps, end-of-line validation, repair procedures, and quality checks for a product that walks, balances, grips objects, and interacts around people. Musk himself has warned that the ramp is difficult to predict. That caveat matters because a prototype doing a task on camera is not the same as a factory producing large numbers of safe, durable robots with consistent performance. The hard part is not making one impressive unit. The hard part is making the 10,000th unit behave like the first good one, at a cost customers can justify. That is why 2026 output would likely sit far below the million-unit dream. Early production would probably be used for learning, validation, factory trials, and Tesla's own internal operations before broad consumer sales. The first goal is not domination. It is proving that the design, supply chain, and assembly process can survive contact with real manufacturing. While Tesla works through that ramp, competitors are not standing still. Other humanoid robotics companies are already shaping what buyers expect from speed, dexterity, safety, service life, and price. That makes Optimus a race on two fronts at once. Tesla has to make the robot smarter, and it has to make the robot manufacturable. The clearest comparison is Boston Dynamics' Electric Atlas, because it shows what the premium end of humanoid robotics can look like. Atlas is designed as a high-capability industrial machine, not a home assistant. Its new electric version is built for strength, balance, and complex movement, with roughly 56 degrees of freedom across the body. That gives it a level of athletic control that makes warehouse and factory tasks look very different from a slow household robot carrying laundry. But Atlas is not trying to become a consumer product at Tesla scale. Boston Dynamics has spent years proving mobility, manipulation, and reliability in demanding environments, yet its business path is more industrial than domestic. That matters because Atlas can pressure Tesla on capability, while not necessarily competing for the same future customer standing in a kitchen. Unitary attacks from the opposite direction. Its G1 humanoid has pushed attention toward lower-cost hardware, with configurations landing in the low to mid 5 figures. Then the R1 raised the stakes again by pushing expectations toward a sub-$6,000 humanoid market. These robots may not match the most advanced systems in manipulation, autonomy, or safety, but they change the pricing conversation. If buyers start seeing humanoids as affordable platforms, Tesla cannot rely on ambition alone. There is also a rival group that often gets left out of the Atlas versus Optimus comparison. Figure AI is targeting commercial labor with partnerships and fast iteration. X is leaning toward home and general purpose use. Aptronic is building humanoids for logistics and industrial work. Agility has already focused on warehouse deployment with Digit. Sanctuary is pursuing human-like manipulation and task learning. Several of these companies may be more direct competitors to Optimus than Atlas because they are aiming at workforces, service roles, or eventual consumer environments. So Tesla's position is powerful, but not protected. Its advantage is the scale story: batteries, motors, manufacturing discipline, artificial intelligence infrastructure, and a brand that can attract attention instantly. Its vulnerability is that competitors are attacking from both sides. Premium robots are raising the performance bar, while low-cost robots are pulling down price expectations. Optimus has to land between those forces and prove it can be useful, safe, and affordable at the same time. The honest answer is this: Gen 3 may be Tesla's most important Optimus step yet, but it has not already proven that it can cook dinner, clean a house, or handle 100 everyday tasks without help. A real reveal should be judged by specific signals, not by one polished clip. Watch for unscripted manipulation where the robot handles objects it did not place perfectly in advance. Watch for safe interaction around people, especially when a human steps close, changes the environment, or interrupts the task. Watch for full task completion without camera cuts, because a robot that only shows the easy middle of a job is not proving the job. The hands may be the biggest clue. Cooking and cleaning depend on grip changes, wrist control, pressure, and recovery from mistakes. A robot has to hold a sponge without crushing it, pick up a plate without dropping it, open a drawer, handle a towel, and use tools that were designed for human fingers. If the hands fail after a few minutes, the whole household vision fails with them. Battery life also matters more than a viral demo. A home robot cannot be useful if it needs constant charging after short bursts of work. Tesla would need to show endurance across repeated chores, not just one impressive task under ideal lighting and a prepared countertop. The breakthrough would not be Optimus cooking one meal on stage. The breakthrough would be Optimus loading a dishwasher, wiping a spill, sorting laundry, carrying groceries, and doing those boring jobs again tomorrow in a messy, real home. That is the standard. Optimus wins if Tesla can turn artificial intelligence, reliable hands, real-world data, and mass manufacturing into one scalable product. Until then, Gen 3 should be treated as serious progress, not proof that the robot butler era has already arrived. So when the next Optimus reveal arrives, do not watch for buzzwords. Watch for useful work, clear autonomy, and repeatable results in normal conditions. If Tesla can prove that, Gen 3 becomes more than a prototype. It becomes a real step toward household robotics at scale. Thanks for watching. Write a comment with the task you would trust Optimus to do first, and subscribe for future updates on Optimus, humanoid robotics, and Tesla manufacturing.